All right, so today I'm going to be explaining another important paper with the title Target Concrete Score Matching, a holistic framework for discrete diffusion. So previous video I talked about this concrete score matching, which was a very good move for discrete data, like tabular data, like graph, like language. Now this paper is application of that to discrete diffusion. So this ICML paper in 2025, that the idea is that discrete diffusion is a promising framework for modeling and generating discrete data. In this work, we present target concrete score matching, a novel and versatile objective for training and fine-tuning discrete diffusion models. TCSM provides a general framework with broad applicability. It supports pre-training discrete diffusion models directly from data samples, and many existing discrete diffusion approaches naturally emerge as special cases of our more general TCSM framework. So this allows seamless integration with reward functions and pre-trained models, which inherently only operate in the clean data space rather than the noisy intermediate spaces of diffusion processes. You need some background on continuous time Markov chain models. That recently these continuous time approaches to diffusion have been very fruitful for many reasons, like their model rate probability matrices. This is similar to that. The continuous time Markov chain is an S-value time-dependent family of random variables that form a Markov chain characterized by the probability transition kernel, with the initial distribution of the process at time 0, which is P0 of x0, and U is called the velocity or the rate matrix, which indicate the speed at which the probability transitions between two states. Remember, in diffusion, we have continuous time or discrete time, also continuous space, a discrete space, continuous time, continuous space. So where you are is very important. Any of the models that we know is in one of these categories. And each of them has some function, has some necessity. It's out of necessity that we do this. We use the discrete flow matching as a general framework to introduce discrete diffusion models. Our goal is to transfer samples from source distribution to target distribution. So the goal is to approximate the velocity using a neural network. So this paper is focused on the flow matching approach, the conditional flow matching approach, where we sample t from distribution omega of t. And here you see definition of Bregman divergence. So the velocity is governed by true denoising distribution. So instead of parameterizing the velocity directly, we can use a model to approximate this probability by minimizing this loss. So this D is just the statistical divergence. For example, you can use KL divergence. Now, what is this target score matching? In previous video, I talked about concrete scores, and so this is a definition of what a concrete score is. And now we want to to say what target concrete score matching is. So our approach builds upon discrete flow matching framework by adopting the data prediction objective. This is a data prediction objective, discrete flow matching. So this objective offers crucial flexibility, remaining valid for various model architectures and naturally supporting different probability paths without structural changes. So we now introduce a target score matching, which aims to align our model denoising distribution with a true denoising distribution by matching their respective concrete scores. So the objective is expectation of these divergence. This divergence between the concrete score. This is concrete score, this is concrete score. We are learning it. And the interesting thing that I liked in this paper is this, they use one Hamming neighborhood, which is a very natural. You know, if you use it for graphs, it's very natural. You can use it for graphs. You can use it for tabular data. This Hamming distance is very natural. For any sequence, the K-Hamming neighborhood is defined as all y's that the Hamming distance between x and that y is less than k. So when applying this TCSM framework to first Hamming neighborhood, where sequences differ by at most one token, we can represent the concrete score as a V by L matrix by replicating the original sequence x L times, with each column defined by this. So by composing objective function that here I said, this objective function, you can compose it into L groups based on their sequence positions. So this objective is termed score-based as it directly operates on concrete scores. Alongside the score-based objective, we propose another objective centered on distribution matching. So this distribution loss you see here is it transitions from matching joint distributions via a concrete score matching to aligning conditional distributions. This objective uses a statistical divergence. Now this theorem here demonstrates that both score loss and distribution loss are effective for aligning the concrete score between two distributions. So to gain more insight into L score and loss of distribution objectives, we examine their respective targets, the concrete score ratio and the conditional distribution. For the score objective, we can decompose targets as this, and this shows that concrete score is a weighted version of P1 concrete score. So these two equations are the most important equations in this paper, because this probability of x1 condition on xt concrete score is a weighted version of P1 of x1's concrete score. And here this C here is just here indexes the concrete score C. For example, we say at position y1. The distribution-based objective reveals an analogous relationship. So it constitutes a weighted transformation within the target distribution space. It can be interpreted as probability normalized instance of the concrete score. Our target concrete score matching and traditional denoising score matching approaches, so these highlight the crucial distinction between them. Unlike denoising score matching, which operates through the lens of noising process, TCSM directly engages with the clean data distribution. So now you can beautifully show for different domains like discrete or continuous, the different approaches that you can use. What is their target objective? What is their target quantity? For example, for target SM in continuous, the score of P1 is the target objective. The gradient of log P is the target quantity. So you see, it's like for the discrete world, we need to have a gradient version of something that is discrete. How do we define it? Why not with this ratio? Or why not with this ratio? You can also condition on x1. So there are different ways that you can have an equivalent gradient log of probability in the discrete world. Because these two, if you look, gradient is only defined for continuous domain. But when you go to this discrete domain, these two are discrete in the discrete domain, then you need to have some creativity to make some objective very close to that, some approximation. There are hundreds of approximations that you can define. This is just one of them. This concrete, your concrete can be another thing. So there are many rooms for improvement of this interesting idea. For the distribution-based objective, it is straightforward to derive a simple objective when using forward KL divergence and P1T as the proposal distribution. So they did some experiments like this halo transformer, pre-trained BERT. For example, here is interesting. Unlike previous approaches operating in noisy spaces, our method focuses exclusively on clean data at t equal to 1. This perspective creates a valuable connection between TCSM diffusion and other models trained on clean data. We can leverage the pre-trained models like BERT or autoregressive language models to estimate this probability. While BERT directly provides this distribution through mask token prediction, autoregressive models require marginalizing over the vocabulary